I've got an electric circuit here. It's one of the ones you saw from the last video. The only thing that's different is that instead of a battery, I have these red and black wires, which are plugged into our classroom's lab power supply. They take the place of the battery. The red wire acts just like the positive side of the battery. It pulls electrons out. And the black one acts just like the minus side. It adds electrons in. So electrons are flowing through the light bulbs because of the power supply or the battery. It's nice to have this because it means we can set really any voltage we want, and also it saves on wasting batteries. So if we were going to try to communicate to somebody what's going on with this circuit, how would we do that? We could try to describe it, but that could get confusing pretty quick because most circuits are a lot more complicated than this. So the easiest way to tell someone about a circuit you've built is to draw it. Now, you don't draw a nice artistic picture showing all the dust and stuff on this and the shapes. You draw just the bare essentials that someone could build it themselves. That's what's called drawing a schematic. So let's draw a schematic of this circuit, paying attention to how the wires are connected. I could mess this all around, move it in all sorts of different directions, change it. It's not fundamentally going to change the order in which the parts are. So that's all we're really going to care about in a schematic. So the most important thing is clearly the power supply. So we'll start with that. And we'll use a symbol to represent it. This symbol is really commonly used. It's two parallel lines. The longer one is the positive side. The shorter one's the negative side. And then we draw the wires coming out of each. Let's start at the positive terminal and let's walk our way around our circuit. So the wire coming from the positive is connected to a light bulb. So we'll draw a symbol for a light bulb. And that's one of the wires that goes into the light bulb. The other one goes and gets connected directly to another light bulb. Now I know there's the alligator clip in the middle, but we don't have to draw that because all it's doing is connecting our two wires. So there's our other light bulb. And then out of this light bulb, it goes to the negative. So that's the schematic of this circuit. Let's take a look at a couple of other schematics. So this is a really similar circuit to what we had before, but I've added in a switch. So I've put a list of commonly used symbols up here. Let's see what's going on with this circuit. So again, we'll start with our power supply. So we have our positive and our negative. From the positive, we go to a light bulb. And then we go from the light bulb through the wire, which is kind of loop-de-looped, but we go to a switch. We don't care about the loop-de-loop. We just care about the connection. And then this is the symbol for a switch. It kind of shows what the old knife switch looked like. And then we go from the knife switch, we'll follow this wire to our other light bulb. Again, we don't care about the shape. We're just trying to show what the connections are. And then from this light bulb back to the power supply. So that's our schematic for this circuit. Let's see how we can keep track of how energy changes as we go around a circuit. And maybe come up with a reason on why electronic devices act the way they do. Just one thing that's a little bit confusing. We know, living in the 21st century, that electrons are being added at the negative side and taken away at the positive side. So you think it would make sense to say electric current goes in this direction, from negative to positive. Unfortunately, back in the day when they were first investigating this, we didn't know what an electron was. So they defined current as leaving the positive, going through each element of the circuit, and then going back to the negative. We call that I for current. It's a little bit confusing, but that's how we're going to discuss the flow of electric current through these circuits. The first big thing we have to ask ourselves is, why is electric current flowing through these circuits? Well, there must be some sort of energy input, and we know it's that electrons are being added here and taken out there by chemicals actually being consumed. So the wires coming in here are pushing electrons through the circuit. They're pushing charges through the circuit. They're doing work on charges. And I think you guys know that the power supply is obviously the energy source. How can we measure this push? I'd like you to think of it in terms of potential energy. Let's imagine a positive charge. And again, we're pretending it's positives moving through the circuit. Let's imagine a positive charge sitting right here. Imagine this is you, and you've gone for a hike. You parked your car at the base of a mountain. And then somebody did work on you, or you did work, I guess, walking up the mountain. What would you have gained? You would have gained potential energy. So to figure out how energy divides up in this circuit, we really need to measure from here to here to figure out how much work was done. What happens to your charge after it gets through the battery? Same thing would happen to you if you walked up to the top of a mountain. You then would come back eventually to where you started, to your car. So in this case, that would be passing through each of the devices that use energy, and that would get us back to where we started. So it all depends on how much energy do we put in. Now, of course, you guys know that's a loaded question. How long is this going to run for is going to affect how much energy. So what we're really interested in is the electric potential, or the voltage. The potential energy that each coulomb of charge gets as it goes through the circuit. So imagine that's a coulomb of positive charge. What kind of work did the power supply do to get it up there? If it was actually a mountain you hiked up, maybe you'd use some sort of measuring tape or something to figure it out. But you'd measure from where you started to where you finished. And that's what we're going to do here. I have a voltmeter, and you'll notice that there's a negative side and a positive side on it. And what we're going to do is we're going to connect the negative side to the negative side of the battery. We're going to connect the positive side to the positive side of the battery. And we're going to let the voltmeter tell us how much energy each coulomb of charge gains as it gets pumped up by the battery. Voltmeters always get hooked up across the circuit. So take my positive, we'll hook it up here. We'll take my negative and we'll hook it up here. And according to the voltmeter, we've got 5 volts, 5 joules for every coulomb that rises. Apologies for the twitching. These wires are not in all that tight. So that's how we figure out how much energy each charge gets as it goes around the circuit. voltage is what pushes the charges. And we measure voltage across a circuit. So in order to figure out how many joules per coulomb we had, how much work the battery did on each coulomb of charge, we had to put a voltmeter across the circuit from the bottom of the battery, the negative, to the top of the battery, the positive. But there's another important thing we need to know, which is how fast our charge is moving through the circuit. That's a little harder to figure out. Whereas you could measure the work a person would have to do hiking up a mountain by just measuring the mountain and measuring from the top to the bottom of the mountain, just like we did with the voltmeter. Knowing how fast that person's moving on the mountain, we'd have to somehow look at the individual person. So how do we look at the individual charges? Instead of measuring across with an ammeter, we actually measure through. So let me show you what I mean. In order to get the current going through this circuit, I'm going to take our power supply. I'm going to wire to our first light bulb, just like we have. But then, instead of going to our second light bulb, I'm going to go to the ammeter first. Then I'll go to our second light bulb. And back home to the negative. So what that means is the current actually has to pass through the ammeter in order to measure. So let's set that up real quick. Notice the voltmeter is still reading 5. I'm actually going to break the circuit apart. So now no electricity is flowing. Although look at the voltmeter. It's still reading 5. And the reason for that, of course, is that the power supply still has 5 volts across it. The power supply didn't cease to exist just because I just stopped letting current flow through the circuit. So this is sitting there telling me it's ready to give every coulomb 5 joules. But as the light bulbs are out, clearly nobody's getting any joules right now. So just going to take my ammeter and we'll hook up the positive side of it to this bulb. And we'll hook up the negative side of it to this bulb. And notice our light bulbs are back on. The current's flowing through the meter. And we're getting a current of, looks like about 8.08 amps. So those are the two key pieces of information that we need in a circuit to figure out what's going on with the charges. We need to know how much energy each charge gets, and we do that with voltage, which is measured across the circuit. And we need to know how fast the charges are flowing, which we do with current, which is measured through a circuit. I've used these two antique meters here for a very specific reason. They look pretty different, and that way you'll be able to keep track of the difference between the voltmeter and the ammeter. More modern ones look identical and sometimes can even be the same meter. So using these in this video will help you know which one's giving us energy per charge, voltage, and which one's giving us the speed of charge flow or current.